Hi everybody, so I'm Alex Bradbury. I work for low-risk CIC. I think we've spoken at every RISC-V workshop so far on a variety of topics. Today I'm focused on the compiler work we've been doing, specifically building towards a production-ready RISC-V LLVM toolchain. Now, first of all, everybody's asking me, in fact, at the workshop and just previously, LLVM and Clang versus GCC, why do I care about one versus the other? So I don't want to create any friction between the different communities, but I just thought I'd give a very brief rundown of the reasons why some people might choose one versus the other. So if you are an end user, you might be interested in LLVM and Clang because it supports a language you're interested in, such as Rust, Julia, or Swift, which are implemented with LLVM as the default compiler backend. Historically, Clang has done very well in terms of compilation time and error messages. It's actually been a real success that Clang started off with those advantages. GCC has caught up to a certain extent, so there's some great competition between the two projects. Many companies are interested in LLVM and Clang, one reason being the licensing, in that they're under a permissive BSD-style license, unlike the copyleft GPL licenses used by the GNU toolchains. Additionally, LLVM and Clang is implemented in a fairly well-structured modern C++ code base, which is one aspect which has attracted a whole bunch of engineers and companies towards it, even those who aren't particularly bothered by licensing one way or another. So you'll see the majority of compiler research being done these days in universities using LLVM and Clang. And it's possible to use it as your standard system compiler. Google just gave a really interesting talk at the LLVM workshop last month about using it as the default compiler for the Linux kernel and complete Android user space. Now, most people's conversations with me, they kind of these days seem to leap straight into this, so I thought I'd do the same. It's normally, hi Alex, how you doing, and how is RISC-V LLVM going? So I'll just dive straight into the current implementation status. So I talked about this a little bit at the last workshop. Pleasingly, I was able to attract some support from a RISC-V Foundation member to fund the work full-time since July. So it's been a relatively short amount of time of full-time work, but we've managed to make incredibly rapid progress in that time. I've been using the GCC Torture suite as a sort of litmus test to see how it's going, which is a suite of about 1,400 to 1,500 tests, depending on whether you compile all those which use GCC-specific extensions. And we have CodeGen passing 100% of that across RV32i with the M, F, and FD at all optimization levels, as well as RV64i. And there's just a little bit more work to do to actually verify it across with all the additional extensions. You can also see the current status of the port at any time by looking at GitHub. And I should say that's just a handy place to track the maintained patch set and the current status. The whole purpose of this project, as I'll be talking about a little bit more, is to do this all upstream and get it merged into the upstream LLVM code base. And so a lot of the effort has been focused on getting things correct and building up this backend that's able to compile a large and varied variety of inputs. I'm now getting to a point where I'm putting more effort into benchmarking and performance testing and running larger applications. So I haven't done much work with spec yet, but I've had feedback that another group have been evaluating this, have had the majority of spec compiling and working, and just running some fairly small computationally intensive benchmarks. So the benchmarks that Michael Clark used for the RV8 dynamic binary translator, I'm seeing plus 20% here, minus 20% there, which, given that the focus has just been getting it working and I haven't put really much effort on improving performance, that sort of shows that we're in the right ballpark as a starting point. And of course, over time, that will develop much more. As I'll be talking about later, the upstreaming of this work is ongoing. And a really pleasing thing that's happened over the last couple of months is that we've had more people get involved and start contributing. So I'm very grateful to Andy's Tech for the work they've been doing on the LLD, which is the LLVM linker, as well as MC layer support for the compressed instruction set. So that's the high-level status. Okay, you've got the answer to that question now. We can perhaps take a step back and look a little bit at the nature of the work that's been done. So implementing support for RISC-V in a project like Clang and LLVM, it touches a large portion of it, but not everything. So I perhaps didn't say earlier, Clang, in case you're not familiar, is the C language front end for LLVM. So LLVM is your compiler backend, Clang is your front end that parses C and C++. And so I took the approach of working bottom up, so starting with the MC or machine code layer, which handles the assembler, disassembler, and encoding of the instructions that were selected by CodeGen, and then encoding them appropriately for the RISC-V ISA. Once that was built up as a solid base, I then started implementing CodeGen step by step, adding in a very large and extensive suite of unit tests targeting each feature as it's added. And then for the middle end, so the bit that does analysis and transformations on the compiler intermediate representation itself, the LLVM-IR, that's actually one bit that needs very little work at all. It's one of the reasons you'd be attracted to a project like LLVM, because you get all of the hundreds of engineer years that have been invested in a whole range of advanced analyses and transformations effectively for free. Now, in practice, there are a few target-specific hooks that you want to enable, or a few cases where the middle end is doing an optimization that then makes things much harder for you later on. But certainly there's a lot that you can build on there. And then for the Clang front end itself, as you'd imagine, you get a huge amount of, the vast majority of it is completely reused. It's target independent for code for parsing C and C++ and generating LLVM-IR. However, there's some amount of work to support the RISC-V command line parameters, as well as the defines that get set and the RISC-V ABI in general. That's actually a little bit of somewhat target specific, exactly how you take your C function definition or C++ and then generate appropriate LLVM-IR for it. There's a little bit of work to do there. And now I thought I'd go through some of the challenges and the ways in which I've addressed those challenges while working on this. So the first one is really getting the project off the ground, and I mean bootstrapping in the general colloquial sense rather than the compiler-specific bootstrapping term. So one of the challenges with starting any project like this, I guess similarly for the Linux kernel or something like that, is how starting from scratch, starting from nothing to produce, we know where we're heading, which is we want to produce a high-quality compiler backend that has the level of sophistication of the AArch64 and x86 backends, but we wanted to start with something that's relatively simple. And it's very common to start by copying and pasting code from another backend that looks sort of similar, or at least it's nice and small and easy to work with. Now I've been working with LLVM and Clang for a long time, so about 8 years working on LLVM backends, and I've done a lot of work with an outer tree backend that started off with this path, and it leads to an awful lot of technical debt that can be quite hard to undo over time. So I really taken a very conscious effort to invest extra time up front to do this as cleanly and in as step-by-step way as possible. So actually, I think possibly for in ways that haven't been done quite so much in the LLVM community, trying to pick out the bare minimum working slice of an LLVM backend that you need, and then incrementally adding features to support the different aspects of code generation that we need. Another ongoing challenge is also one of the great advantages of the RISC-V ISA, which is that it's a general purpose ISA that comes out of the box with a suite of standard extensions, as well as a number of options about how which of those that you implement, as well as a possibility to implement your own extensions. And that's great, and it's one of the reasons that many of you are attracted to RISC-V, but it's also causes more work for the poor compiler engineer who has to support all of these different varieties, the different variants of the soft and hard floats, ABIs, as well as the different instruction set variants. And I guess partly that's been addressed by, in terms of implementation style, so the RISC-V ABI is nicely specified so that it's parameterized by the width of your floating point registers as well as the width of your GPRs, so you can kind of reuse the same code path just with those two things as parameters. I've also been able to make use of more recent work in upstream LLVM to enable parameterizing the whole backend by the register width, which drastically reduces code duplication versus previous RISC-V LLVM work, as well as, in fact, all the other upstream LLVM backends who haven't switched over to using this scheme yet. So testing is hugely important in order to make sure that particularly when implementing a backend, it's very easy to make a change which breaks something else. So you need a very strong set of unit tests that help to pinpoint exactly what changed if something, and well, what broke once you make that change. So the targeted unit test has been incredibly important, as well as the GCC torture suite as a sort of litmus check to check that we're generating code that is sensible and executes. I've also put effort into developing new tools to help to better support the sort of testing work that I'm doing. So we have this range of different ABIs support, and in fact more if you add in the Q extension. And so I wrote a tool called ABI Cop, which aims to act as a sort of golden model of the RISC-V ABI, as well as supporting test case generation. It currently supports test case generation across linking different compilation units across GCC and Clang, but its I intend to improve that to really achieve what the main purpose was, which was to use it as this golden model so that you can test either Clang or GCC or perhaps your Java JNI interface or Rust or whatever else it is that you're trying to have that aims to comply with the RISC-V ABI in isolation and against a model that aims to be sort of give the Oracle golden model answer. And I think testing is one of the key areas where people can, certainly the wider RISC-V community can collaborate on, and where I think the LLVM effort can help to move forwards other projects in the RISC-V ecosystem, such as GCC, such as these other language ports. So as I say, I'm moving towards doing larger scale integration tests. The next obvious step is doing automated compilation testing against a huge corpora of software, such as the Linux user space stack, FreeBSD base system. We want to be able to have work with confidence that the compiler that we're using today is generating code that was just as correct as yesterday and also performs as well as it did yesterday, or hopefully a little bit better, which is why it'd be good to track that performance over time. And I think you'll probably have to talk to me about it later, but there's a whole range of interesting ways we can, the LLVM community in particular have been applying fuzz testing, and I think we can also make use of that for targeted testing for the RISC-V backend. Now, one of the key challenges I saw, and actually one of the main reasons I got involved with trying to push forward RISC-V LLVM work, was that we could see that there was lots of interest in LLVM and RISC-V, and lots of people were doing work with it, but it was often, we weren't really getting the benefits that we hoped for with RISC-V, which is a shared technology investment in a common base. Companies were taking an initial RISC-V port and maybe doing a fairly short-term R&D project, making the changes they needed, and then it was just sort of, nothing was making its way back upstream, and the port wasn't quite in a form that would make sense to upstream into LLVM. So one of the key ways I tried to do this is to make it much more accessible for your average computer architect or software engineer to get involved with compiler development. So if you look on the GitHub repository, you'll see that there's extensive documentation talking you through step by step exactly how the MC layer was implemented. I'm also expanding that to cover every aspect of code generation. And this is important not just for pedagogical purposes in universities, but I think it should be incredibly useful there, but also so that your average engineer can rapidly get up to speed with exactly the exact design decisions were taken, and indeed LLVM backends in general, which are, it's actually not that difficult to get started with LLVM backend development. It's just up to now been fairly opaque and perhaps not as well documented as you'd like. As part of our efforts, I maintain and what you'll find on that GitHub link is sort of a fictional history of what the LLVM backend looks like. If you imagine that I did everything exactly right the first time, because of course when you write a large project like this, you might start with one approach. You find a few months later that there was a fiddly bug and actually needed to rewrite it. And so it's, as somebody who wants to learn how it's implemented, trying to trace that history and all these changes where you've tried one way, you've tried another, it's not very useful, which is why I've been maintaining this as a ongoing reference for anybody who wants to better understand how it was implemented or how any LLVM backend is implemented. So avoiding this duplicated effort that we've been seeing has been a key goal, and I'm pleased to say we've seen that now. Every RISC-V community member I know of who had previously had outer tree backends are now either actively working on this or looking to rebase their work on top of it and start contributing upstream. We've seen that with the Andy's tech contributions I mentioned before, companies such as Qualcomm through Code Aurora or NXP, Andy's and Codasip are also been contributing to this. We've also had a community member who's very recently got a Rust port up and running, which is really exciting. An additional challenge has been specifications and standardization. I mentioned the ABI, and of course, even since the early version of the RISC-V spec, there was a very concise description of the RISC-V ABI. But of course, the best way of testing these descriptions is actually to go and try and implement it. And then you rapidly find that things that perhaps the original author thought was clear weren't. And so as a process, as part of implementing the LLVM backend, we've managed to make a large number of improvements to the upstream ABI docs, where I think which benefit hopefully everybody. I've also started an effort to try and document and standardize toolchain behavior across GCC and Clang, but also with the hope of trying to better standardize the vendor-specific toolchains that are inevitably going to appear. As if people want to do their own thing, that's totally fine, but it would be quite sad if it ended up where every vendor-specific toolchain had a slightly different way of enabling or disabling extensions. So it's not the most exciting document, but I think it's an important effort that we try and get rid of or avoid accidental incompatibilities. And as I say, a key part of this effort has been to try and get it upstream. So right now, about a third of the patches are upstream committed to LLVM. I am the RISC-V LLVM code owner. I've been very grateful to the LLVM and RISC-V community members who've helped to review and improve that code over time. And I think we're now, particularly now, a number of other companies are starting to actively put engineering effort into validating and testing those patches. We're making quite rapid progress on getting that merged upstream. And this is important because I know many companies have all sorts of policies about using code where grabbing something off GitHub isn't necessarily an attractive option that has to go through legal, whereas and also in terms of maintainability, you want to know that it's something that is up there in LLVM as a standard default architecture. So we're making rapid progress there. So I can actually, I guess, summarize this more concisely, which is to try and do it well, do it definitively, and to grow a community who's going to work on this alongside me, as this is something that I think we've been able to make very rapid progress in the last few months, but over time we obviously want this to be an effort that spans the whole RISC-V ecosystem, which is where we're starting to see. So this work has been done through Low Risk CIC, which is a not-for-profit that I co-founded about 4 years ago. The aim is to serve a community of people who are interested in open source hardware and software. We've obviously been involved in the RISC-V community from day one, and I think this is an example of where Low Risk can fulfill a role not dissimilar to Linaro in the ARch64 ecosystem, with the advantage of covering reference hardware designs as well as software. We see ourselves as, particularly in this case, investing extra effort to unblock something which had been holding back the wider RISC-V ecosystem. So we've targeted high-quality engineering work and then also building a community around it to make sure that it's sustainable over the longer term. So we're dependent on the financial support of other members of RISC-V ecosystem, but we're very keen to expand this effort sustain and expand this effort on RISC-V LLVM, but I also think that the sort of approach and the blueprint I've taken here with LLVM could also be applied across a whole range of other aspects of the RISC-V ecosystem. In terms of statistics for the RISC-V LLVM backend, we're currently at about 20,000 lines added, about 45% of that being code, about 55% being tests. Perhaps an interesting statistic is the number of lines you need to pass 100% of the GCC Torture suite at just supporting RV32i, which is actually only about 12,000 or 6,000 just if you're counting the lines in code, which is actually quite useful because that tells you around about the figure that you need to get somebody started on LLVM development. If you want to understand completely end-to-end how to do a basic compiler backend, and that's about the amount of code that you might want to study and understand, which is actually an amount that's quite feasible to cover in something like a master's course. So we now have engineers from at least 7 different companies actively engaged or about to become actively engaged in upstream RISC-V LLVM development, and it's still at the point where maybe about 90–95% of the code has been authored by me, but hopefully over the next few months we'll hit that very important tipping point where, as a successful open source project, the vast majority of the work will be done outside of low risk and by other companies and individual contributors who are building on top of it. So the next steps for this backend are to continue the upstreaming process, to expand testing across to realistic real-world Linux applications. I expect we'll be running spec as a fully supported workload by around Christmas time, and in the new year I'd hope to, funding allowing, to continue expanding support across, working with the other companies who are interested in supporting the compressed instruction set, as well as fleshing out support for other LLVM family projects such as compiler RT, the LLVM debugger, and beyond. I also think there's a great opportunity to work closely with the various RISC-V working groups, such as a vector extension working group, bit manipulation, to really get continuous feedback on the compiler aspect of this work. It's also an area where being open, as a lot of vector work has been from the start, is a real advantage because there's a large community of very talented compiler engineers who have an insane amount of experience trying to target compilers for every vector architecture that exists previously. So that's a great resource that we can tap into in order to get feedback on the ISA extensions that we're developing. And so the RISC-V LLVM project is ambitious. You don't need RISC-V is a good compiler target, so you don't need a huge amount of ambition just to get basic code generation working. So we're kind of sticking all the ambition directly into producing best-in-class documentation, in ensuring that it's the easiest possible way to get started with compiler development in general, and in LLVM in particular. And the ultimate goal is that it will be the highest performing RISC-V compiler, and as I said earlier, right up there with AArch64 and x86 in terms of sophistication. So if I were to make a kind of a bold prediction or a bold aim, it is that a large proportion of the people in this room in 6 months' time will be building on top of this work and using it as the system RISC-V compiler for your RISC-V projects. And with that, I'd like to thank everybody who's been contributing to this work so far in terms of code reviews, patches, or other supports. And please find me afterwards, and I'd be happy to talk more. Thank you.